In this lesson, we're going to take a look at a new kind of way to take derivatives called implicit differentiation, and we'll be using that on equations that don't quite look like our regular looking equations, but more on that to come. Okay, before we get to the process of implicit differentiation, we first need to understand a few things. So just as a quick review of what a function is. A function is just a correspondence between two sets that assigns each value in the first set to exactly one value. That's the key, exactly one value in the second set. So of course we can draw a little squiggly line here and call it a function. And we know the definition of the derivative gives us the ability to take derivatives of functions, but not relations, which we'll talk about in a moment. So of course, derivatives are just the visual representations of slopes of tangent lines. And of course, there's many different slopes along this function that is drawn. But implicit differentiation is going to help us to take derivatives of equations that are not functions, or in other words, relations. So what do relations look like? Well, first, a relation is just a correspondence between two sets. It doesn't have to have one set exactly having one value in the second. This is kind of a ridiculous case of a relation, but it is a relation. And the reason we know it's a relation and not a function is it fails, if you remember back from algebra, the vertical line test. If you draw a vertical line and it touches the graph in more than one spot, it's not a function and it fails that vertical line test. But does that mean we're not interested in finding derivatives? Well, no. You can see all over the place, even on this squiggly graph, which isn't a very realistic graph, but you can see all over the place there are a bunch of tangent lines, which we might be interested in finding the slopes of those tangent lines. A little bit more realistic case would be a circle, which is not a function. It fails the vertical line test, but nevertheless it still has tangent lines all around it, and we would be interested in finding the slopes of those tangent lines. Okay, so we have to make sure we know a few things before we get into this implicit differentiation. A quick review of some vocabulary that we talked about. Whenever you see the notation dy dx, we're saying that that is the derivative of y with respect to x. In other words, it's a noun because it is a thing. That is the derivative. On the other hand, when we write just a d over dx, d dx, that's telling us to take the derivative of whatever function we have with respect to x. So it's a verb. It's asking you to do a action. So an easy example here, but I'm going to use it to kind of build up to the idea of implicit differentiation. We have our function 3x squared minus 4x plus 1. I want to find dy dx. That is to say, I want to find the derivative of y. dy dx is just another way of saying the derivative. So let's find y prime. Real quick and easy to do. 3x squared is 6x minus 4, and that's it. That's our derivative. So I'm going to kind of take a bunch of extra steps to get to the same answer. I'm going to show the derivative, but with every little tiny step I can show. Again, kind of helping us build up to the process of implicit differentiation. So the first thing I'm going to do is I'm going to put the notation d dx to indicate what? Well, that's going to indicate that I'm going to take the derivative of everything inside the parentheses. So we know this back from our algebra days. If we do something to one side, we need to do it to the other. So I'm going to put a d dx on the left side with y. I'm going to put a d dx on the right side with our function. So on both sides, we're being asked to take the derivative of each of those sides. So how do we take the derivative of y with respect to x? Well, that's just what we call y prime, or what I wrote as y prime above. Instead of writing y prime, I'm going to write dy dx. Same thing. It still means that's a derivative, but I'm writing it in that different notation. d dx, taking the derivative of y with respect to x, gives us dy dx. On the right side, I'm going to go ahead and take the derivative of each of the terms of the expression. So I'm going to take the derivative of 3x squared, I'm going to take the derivative of 4x, I'm going to take the derivative of 1. Why? Well, it's our sum difference rule. We can take the derivative of each of those individually because they're being added or subtracted. And of course, it's as simple as we saw above. 6x minus 4, and I'll just put the plus 0 there to emphasize the derivative of the 1. So what does that give us as an answer? Well, of course, it needs to give us the same answer from above. The only thing different is the notation I used. Instead of putting y prime, I put dy dx. Still means the same thing. That's our derivative. Okay, so moving on to a little vocabulary. An equation in an explicit form is when one variable is directly equal to an expression made up of another variable, or in other words, what I'll call a regular equation, when you have y on the left side and some other stuff with x's on the right side. So again, I'm going to just take this derivative for the practice, but again showing this notation that we haven't really used much yet. I'm going to show that I'm taking the derivative with respect to x on the left side, and I'm going to show I'm taking the derivative with respect to x on the right side. The derivative of y with respect to x is just dy dx. The derivative of x squared with respect to x is just 2x. So nothing's changed. The only thing that's changed is instead of putting f prime of x or y prime, I'm now writing that as dy dx. So what does that lead us to? Well, that leads us to these different kind of equations that you probably really haven't encountered much. And it's an equation that's something called implicit. When you have an implicit equation, neither of the variables that we're looking at are by themselves on one side of the equal sign. What would be an example of an implicit form? Well, it would be something like this: x squared minus xy plus y squared equals 7. And in this particular case, there's no way to solve for y. We can't get y by itself, so that's why we call it an implicit form. Okay, so let's practice taking some derivatives again, but showing the notation a little more technically than we have in the past. So what are we doing here in this first example? Well, we're being asked to take the derivative with respect to x of x cubed. So something I need to point out that we really haven't pointed out before. These two variables agree. We're taking the derivative of an x term with respect to x. So they match each other. They agree, which means we can take the derivative the simple way. Just use the simple power rule. Don't need to overthink it. And of course, that's just 3x squared. But something we're going to start running into more often starting in this section is, what if I ask you to take the derivative with respect to x, but not of a x equation or expression, but what if I ask you to do that of a y, and in this case y squared? Well, in this case, the variables don't match. They don't agree with each other. Now, that doesn't mean we can't do it. All that means is we need to use the chain rule. And that's basically the power rule, but you need to remember this whole u box and u prime and the extra steps that it's going to take. So let's go ahead and proceed. We don't know how to take the derivative of y squared, but if we call that u, we can take the derivative. So that's what I'm going to do. I'm going to go ahead and just take a step to put the y in parentheses, just to emphasize that I have a y inside of a power of 2. So we can't take the derivative since we're taking the derivative with respect to x, but I can call y the letter u. I can do this little u box like you've seen before with the chain rule, so I can get that y out of there. If I get that y out of there, the derivative of it will just become 2y. Just like the good old chain rule, nothing's really changed. We've done this piece of the chain rule. We brought the power down, we rewrote the u, which is y, and we reduced the power by 1. But we need to remember to multiply by u prime. So if we go back to our u box, the derivative of u is u prime. But what's the derivative of y? Well, you might be tempted to write y prime, and that wouldn't be wrong. But we're going to write it, again, with the notation we haven't used much until now. We're going to write that as dy dx. So u prime is equal to dy dx, so we need to multiply by dy dx, and that's the derivative of y squared. So just note, the derivative of y squared is not just 2y, it's 2y dy dx. So that's the thing you're going to have to keep in mind every time you take the derivative of a y term. You can take the derivative just like if it was an x term, but you're going to have to make the addition of a dy dx piece. You're going to have to throw in the dy dx every time you take the derivative of a y term. So we'll have to keep that in mind every time we're taking derivatives. So let's practice another one. In this case, we're being asked to take the derivative with respect to x of x times y. Well, it's great that there's an x there, but unfortunately, the variables disagree. They don't match. X times y has a y in it, and we're supposed to be taking the derivative with respect to x, which we can't do. So we're just going to have to keep in mind again, every time we take the derivative of a y term, we need to put a dy dx with it. So how do we take the derivative of x times y? Well, the key word is times, multiplication. It's a product, and it's the product of two different functions. So we need a product rule. So let's go through the product rule. The product rule says we need to take the derivative of the first term. Well, derivative of x is 1. And then we need to multiply that by the derivative of the second function. The second function, we need to multiply by just the second function, which is just y. Then we need to add to that a kind of reverse in those roles. We're going to leave that first function alone, which is x, and then we're going to multiply by the derivative of that second function. The derivative of that second function is y. We could put y prime, but I'm going to use the alternate notation. The derivative of y I'm going to write as dy dx. So that's the derivative. Of course, we don't need to have the 1 times y. We can just put a y plus x times dy dx. And that parentheses around the dy dx I think is important. It will help you remember that this is one piece together. Dy dx can't be separated. It can't be split up. We need to just keep that together. It's just x times dy dx. So with those examples behind us now, I think we can attempt our first true implicit differentiation problem. I want to find the derivative with respect to x, that's the key here, of the implicit equation y cubed plus y squared minus 5y minus x squared equals negative 4. So you can see right away there's no way you're going to be able to just solve for y and take a derivative the easy way, so to speak. So here's some good news about these implicit differentiation problems. I'm going to kind of give you the process for doing all of the implicit problems you're ever going to see. Every one of these problems has this same process to it. So if you just kind of follow that process and understand that anytime you take the derivative of a y term, you need to put a dy dx, you should be good. So let's go through the process. We need to take the derivative of both sides of the equation with respect to x. And again, that's where our notation is very important. On the left, I'm showing that I'm taking the derivative with respect to x. On the right, I'm showing that I'm taking the derivative with respect to x. So since all of these terms are being added or subtracted on the left, we can take each one individually. So let's get into it. How do we take the derivative of y cubed? Well, we can take the derivative just as if it was an x term. So the derivative of y cubed would be 3y squared. But because it's a y term, we need to throw in the dy dx. Same thing for y squared. We can take the derivative as normal, which would be 2y, but since it's a y term, we need to throw in a dy dx. The derivative of negative 5y, well, again, just like normal. The derivative of negative 5y would be negative 5, but since it's a y term, we need to throw in a dy dx. So be careful. You can kind of get dy dx crazy with these problems if you're not paying attention. On this last piece, will we need a dy dx? Well, no. it is an x term, so the derivative of x squared is just 2x. And with that, we've taken the derivative of the left side. On the right side, don't overcomplicate it. We're just taking the derivative of a negative 4. That's a constant, so that's equal to 0. So remember what the goal is. We're trying to find the derivative. And you just have to remember the way you can write a derivative is dy dx. So we're looking for dy dx. I see dy dx in all three of these terms, so we can solve for dy dx. The next step is to collect all the dy dx terms on the left side of the equation and move everything else to the right side. Luckily, that's only going to involve moving one thing at this moment. The negative 2x we can move over to the right side as a positive 2x. So what does this give us? Well, this gives us the ability to do some factoring. If all of these terms have a dy dx in them, we can factor that out. And remember the goal. We're trying to solve or find the derivative dy dx. So the third step will be to take the dy dx out of all of the terms, factor out that from all of the terms. So if you factor out a dy dx from all of the terms, you're just left with 3y squared plus 2y minus 5. The last step is always going to be the same. Once you factor out that dy dx, we need to solve for dy dx. And since you factored it out of all the terms, we're left with a multiplication. And to undo that multiplication, we need to divide. So we need to take that 3y squared plus 2y minus 5, divide it to the other side, and that's the answer. Our slope machine, our derivative, is 2x over 3y squared plus 2y minus 5. And notice, if you wanted to find the slope, now you'd have to plug in one extra piece of information. Before this lesson, you'd always have to just plug in your x value. But in this lesson, you might be plugging in x's and y's to find slope. Okay, moving on to a few more examples. Here we're given x squared plus y squared equals 1, and we want to find dy dx. So let's jump right into it. This is an implicit form, and we can apply implicit differentiation to finding the derivative. So just like you saw before, the first step will be to show that you're taking the derivative of the left side and taking the derivative of the right side. So let's take the derivative of the left side first. The derivative of x squared is just 2x, but again, don't go dy dx crazy and start putting that everywhere. That's an x term, so it's just 2x. But when you take the derivative of y squared, that's going to be 2y. But we have to throw in a dy dx because of the chain rule, and you saw that a couple slides ago. So just keep in mind, anytime you take the derivative of a y term, you need to throw in a dy dx. On the right side, we are taking the derivative of constant 1, and that's just 0. Next step is to move everything over that doesn't have a dy dx to the right side. And of course, that's just the 2x, so that becomes negative 2x on the right side. Next step is to solve for dy dx if you don't need to factor. And in this case, we only have one piece on the left side, so we can just solve for dy dx, which of course means we'll divide by 2y. The 2's will cancel, and we're left with the derivative, or our slope machine, of negative x over y. So not too bad. The second part of this problem will be using the idea of this slope machine, because we're being asked to find the value of the slope at 2 points, 1, 0, and 0, 1. So I'm going to cheat real quick using the graph of our x squared plus y squared equals 1, which is a circle, by the way, of radius 1. We can see the slope right away at 1, 0 is undefined. It's a vertical line. And at 0, 1, it's a 0 slope. So we already know the answers we should be getting, but let's go ahead and apply using the derivative to find the slope. So there's going to be a little change in notation. In the past, if we wanted to find the derivative, it's usually been f prime or something like that. And we would write f prime of, say, 1 or something like that. And then we'd plug in the 1 and we'd be good. But unfortunately, it's not f prime that we're using the notation. We're using the notation dy dx. So when we use that notation, how do we show that we're about to plug in a number? Well, we're going to use this notation. We're going to write dy dx, we're we're going to put this vertical line, this bar here, and then put at the very bottom the point that we're plugging in. And just as a reminder, of course, that's our x and that's our y. So that's the new notation, so to speak, to show that we're evaluating a derivative using the dy dx notation. Ultimately, once you know that that's the notation, all we need to do is plug in the numbers. We're going to plug in 1 for x, we're going to plug in 0 for y, and when we divide by 0, we know that's not possible, so the slope is undefined, just like you saw in the picture above. Same thing for the point 0, 1. We're going to use this new notation where we're going to write dy dx. We're going to put this vertical line, this bar here, and then at the very bottom of that, we'll put our point that we're going to plug in. Again, that's our x and that's our y. We'll plug in those points. 0 over 1 is 0, and again, we already saw that from the picture. So just an extra problem to practice implicit differentiation, but more so to kind of introduce this new notation of evaluating derivatives. Before, we used to put f prime and plug in a number like 1, but now we have to change it up a little bit. Okay, moving on to another example with some trig here. We need to find the derivative of this implicit function. So let's go ahead and do that. First step will be to show that we're taking the derivative of the left side, to show that we're taking the derivative of the right side. So let's take the derivative of the left side. The left side is a y term, so we'll take the derivative as normal, so to speak, but we need to throw in a dy dx. The derivative of 2y is 2, throw in dy dx. What about the right side? Well, x squared just becomes 2x. It's not a y term, so we don't need to throw in a dy dx. But what about sine y? Well, sine y is cosine y. But you have to keep in mind, every time we take the derivative of a y term, we have to throw in a dy dx. Really, the rest of these steps are just some algebra steps, because now we need to solve for the derivative. We're trying to find the derivative, and again, that's just another way of saying dy dx. So let's solve for dy dx. We need to move everything to the left that has a dy dx. On the right side, we have cosine y dy dx, so we're going to take that and subtract it to the left side. Now that we have dy dx terms on the left side, we can factor out a dy dx. When we factor out a dy dx from 2, dy dx, we're left with a 2. When we factor it out from the second term, we're left with just cosine y. And of course, still 2x on the right side. Now that we've factored out a dy dx, we're left with a multiplication, and of course, the only way to undo that multiplication is to divide. Since we're solving for dy dx, we'll take 2x and divide it by 2 minus cosine y. That's our slope machine. That's what we could use to find the slope at any point if we wanted to. Okay, last example here will involve us finding equations of lines. One line we've already done before, and that's a tangent line. The other line that we're going to find the equation of is a normal line. We'll get to that a little bit later. But either way, we need to find the tangent and the normal line equations for the curve x squared minus xy plus y squared equals 7 at the point -1, 2. So we're trying to find the equation of a tangent and a normal line. So we know what a tangent line is, and you can see that visually there. But a normal line is kind of like a tangent line, but it's not quite exactly the same. A normal line is perpendicular to the slope of a tangent line. So after we find the slope of our tangent line, we're going to have to recall how to find the slope of a perpendicular line, but we'll get to that in a little bit. So very first thing we need to do is take a derivative. We're trying to find the equation of a tangent line, which means we're going to need slope. We already have our x and our y, so we need our slope. So we're going to take the derivative of the left side, we're going to take the derivative of the right side. So let's jump right into it. The first derivative is pretty quick and simple. We're taking the derivative of x squared, that's 2x, and one more reminder, don't go dy dx crazy. Don't throw in those dy dx's unless it's a y term. Okay, Next step is to take the derivative of x times y, which we've already done. If you refer back to a few slides ago, you saw that the derivative of xy is going to be found using the product rule. The derivative of x is 1. We're going to leave the second function alone, which is y. And we're going to switch those roles. We're going to leave the first function alone, which is x, and then take the derivative of the second function. The derivative of y is dy dx. It's just another way of writing y prime. The next term we have to take the derivative of is y squared. Again, we've seen that already. The derivative is 2y dy dx. And then on the right side, don't overcomplicate that. The derivative of a constant is just 0. Okay, so we should try to simplify this a little bit. We can take this negative and distribute it to both of those terms. We'll get negative y minus x dy dx plus 2y dy dx. Our goal is to figure out what the derivative is equal to, which is our slope machine. So we got to solve for dy dx, which means we need to move everything over to the right side that doesn't have a dy dx. That would be the 2x and the negative y, which becomes y minus 2x. Now we're left with two things on the left side that have a dy dx in them. So we can factor out a dy dx. If we factor out a dy dx, we'll have a multiplication. And so that we can undo that multiplication, in other words, solve for the dy dx, we can just divide. So our slope machine is y minus 2x over 2y minus x. In the past, it used to be very simple, maybe, slope machines, but now it's a little more complicated, maybe. And the other thing to note is it's got x's and y's. So when we try to evaluate our slope, we're going to have to plug in the entire point with the x and the y. So let's go ahead and do that. Let's find the slope of our tangent line. So again, here's our notation. We're going to put a dy dx, we'll put this vertical bar, and then at the bottom of that bar, we'll put the point that we're about to plug in. Of course, that's our x and that's our y. So if you take the x of negative 1 and the y of 2 and plug it in and evaluate that fraction, you'll find that becomes 4/5. So great. Now we can write the equation of our tangent line. We know the point that we're writing the equation at is negative 1, 2. So we can plug in 2 for y, and we can plug in negative 1 for x. And we just discovered that the slope of this tangent line, using our derivative, our slope machine, is 4/5. Like you've seen in the past, it is perfectly acceptable to stop right there if this is free response or something like that, and box that as your answer. But again, just to give you the practice of seeing how to simplify these in case you would have to, I'll go ahead and simplify this down to y equals mx plus b format, and that's our final answer, 4/5x plus 14/5. So what about our normal line? Well, it's still an equation of a line. We're still going to use the point slope equation. We're still going to plug in the same x and the same y, but how do we find a perpendicular slope? How do we take a slope and make it a perpendicular slope? Well, you're going to have to remember one little thing. What you have to do to find the slope of a perpendicular line is do the opposite reciprocal to the slope you have. In other words, we need to make the sign opposite and apply a reciprocal to that fraction. So what is the slope of a perpendicular or normal line to this slope of 4/5? Well, that would be negative 5/4. It's opposite because it's negative, and we applied a reciprocal. 4/5 becomes 5/4. And then everything is pretty much the same as a tangent line. Again, this would be acceptable to stop and circle. But again, I'm going to go ahead and take a step to simplify this and get it down to the final answer of negative 5/4x plus 3/4. So just keep in mind, perpendicular or normal lines are pretty much like tangent lines. They just have an opposite reciprocal slope.